When examining the relationship between two quantitative variables, we've seen some situations where a linear model is not appropriate, and some situations where the conditions that are required to carry out inference on the slope don't appear to hold. In this video, we'll look at how a transformation of the data can sometimes improve these situations. Here's an example where it should be clear that a straight line is not the best model for the data. The Scatterplot shows life expectancy versus GDP per capita for most countries in the world. GDP is a measure of wealth. It seems reasonable to expect that wealthier countries with higher GDPs will, as a result, have longer life expectancies. And looking at the Scatterplot, it does seem that countries with high GDP tend to also be the countries with higher life expectancies. But the relationship is definitely not linear. Mathematically transforming data and statistics can serve many purposes, including turning relationships that are curved into relationships that are linear, so that linear regression methodology can be applied. The particular transformation that we'll look at in this video is the logarithm, which is the most commonly used transformation. It's the most commonly used because it is effective in many situations in producing transformed data that are easier to work with than the original data, and because it gives results that can be easily interpreted. We'll see examples of both of these reasons in this video. Typically, statisticians use the natural logarithm or base E logarithm, but the base 10 logarithm works equally well, and for simplicity, that's what we'll work with here. Let's review some facts about the base 10 logarithm. By definition, if the base 10 logarithm of some number a is equal to another number b, that means that a is what you get when you raise 10 to the power of b. So the logarithm gives us the exponent. Using this fact, the base 10 logarithm of 10 is 1, the log of 100 is 2, and the log of 1,000 is 3, and so on. A useful property of logarithms is that the log of a times b is the log of a plus the log of b. This will become important because it allows us to do the following. If we add 1 to the log of x, that is equivalent to adding the log of 10, since that's 1, which is equivalent to taking the log of 10 times x. We'll use this fact later. Now back to the relationship between life expectancy and GDP, here's why the logarithm transformation will be useful to us. The distribution of GDP is very right-skewed. Many countries in the world are not very wealthy, with low GDPs, and there are few countries with high GDPs. And here's a sketch of the logarithmic function. It changes quickly for small values close to 0 and changes slowly for larger values. As a result, the log transformation of a variable will spread out the small values and bring the large values closer into the other values. So, if we take the logarithm of a variable that has a right-skewed distribution, the result is a transformed variable that has a distribution that is often closer to symmetric. Here is a histogram of the log transformation of GDP, and we can see that it is much closer to symmetric than the untransformed GDP. So now we'll proceed and work with the log of GDP. For comparison, here are the scatter plots of life expectancy versus GDP and versus the log of GDP. The values of the log transformed GDP are more spread out, and we can now see a linear relationship. So we'll work with the log transformed data. Using the method of least squares to find the regression line, we get a line with an intercept of 12.26 and a slope of 14.93. And there is very strong evidence that this slope is different from 0. The p-value for the test of the slope is very small. Interpreting the slope requires a little more care when we've transformed one or more of our variables. In general, in regression, the slope tells us how y changes on average when x increases by 1 unit. So when the log of GDP increases by 1, life expectancy increases by an average of 14.9 years. But what does it mean for a log of GDP to increase by 1? In order to answer this, we need this property of logarithms. Adding 1 to a base 10 logarithm is equivalent to multiplying its argument by 10. So our slope of 14.9 years is the average amount that life expectancy increases when GDP is multiplied by 10. Interpretation of log transform variables typically involves talking about changing variables by multiplicative factors, such as multiplying GDP by 10. Like GDP, many variables tend to grow in a multiplicative rather than additive way, and the log transform versions of these variables often work well in statistical models. Before we leave this life expectancy GDP example, you may have noticed that there are a few points that don't fit the regression line well. Looking at a plot of the residuals versus our predictor variable, we can see that the corresponding residuals are large in absolute value. The linear relationship between life expectancy and log of GDP does not explain well what's going on in these countries. If you're wondering what they are Swaziland, Angola, South Africa, Botswana, and Equatorial Guinea. These are countries with lower life expectancies than their GDP predicts, and there's typically a good reason why. For example, Equatorial Guinea is a large oil producer which has created wealth, but it's not distributed equally. Equatorial Guinea ranks quite low on the United Nations Human Development Index. Less than half of its population has access to clean drinking water, and 20% of children die before age 5. In Botswana, mining of gemstones and precious metals contributes to its wealth, but it has a relatively low life expectancy, in part because 1/4 of its population is infected with HIV. So as we see, while the linear relationship explains much of what is going on with these data, sometimes the points that aren't explained well by the model also tell an interesting story. We'll now look at another example where a log transformation helps us meet the conditions of linear regression. In the life expectancy GDP example, we log transformed the predictor variable to change a nonlinear relationship into a linear relationship. In this new example, we'll log transform the response variable. This example uses the nutritional information that was collected on food items sold at Starbucks in the US in 2011. At that time, the display in Starbucks restaurants listed the calories, but not the other nutritional information. And we'll investigate whether the calorie content, the explanatory variable, is a good predictor of the amount of carbohydrates, which is our response variable. Here's a scatter plot with the amount of carbohydrates in grams on the vertical axis and calories on the horizontal axis. And we can add the regression line and take a look at the plot of the residuals versus the explanatory variable. In both the scatter plot and the residual plot, we see that the variability in the amount of carbohydrates is greater for foods with higher calorie content. So the variability is not constant, and this violates one of the conditions we need satisfied if we want to carry out inference on the slope. Now let's look at what happens when we take a base 10 log transformation of the response variable. There's still lots of scatter, but the variability or spread in the y seems closer to the same for all values of x. The residual plot looks mostly like random scatter, except for a few unusual points with large negative residuals. We'll come back to those. And the normal quantile plot looks close to straight, so we should feel comfortable using our inferential procedures here. Although it may also be worth investigating whether those unusual points are influential. To interpret the slope when the response variable has been log transformed, we can take our estimated equation and raise both sides to the power 10 to undo the log transformation. This gives y is equal to 10 to the exponent of our estimated intercept b0 times 10 to the exponent b1, our estimated slope, times x, our explanatory variable. So then increasing x by 1 is equivalent to multiplying this expression by 10 to the exponent b1, our estimated slope. So we're changing y by multiplying it by 10 to the exponent b1 when we increase x by 1. For this particular regression, the estimate for the slope is b1 equals 0.00122. And 10 raised to that power is 1.0028. And we can interpret this as follows. An increase in calories of 1 is associated with multiplying the amount of carbohydrates by 1.003. So in other words, an increase in calories of 1 is associated with an increase in carbohydrates of about 0.3%. Once again, we've seen that the interpretation of log transform variables typically involves talking about changing variables by multiplicative factors. And in this case, that's multiplying our y by 10 raised to the power of the estimated slope. As is often the case with real data, there is a little more to the story. Here's the scatterplot and residual plot for our model using the log transformation of the amount of carbohydrates. As we noted earlier, the residual plot is not quite symmetric about 0. The positive residuals are at most just over 0.2, but the negative residuals have a couple of values that are much smaller than negative 0.2. One's even smaller than negative 0.3. These residuals come from points that don't fit the line particularly well. Since the residuals are negative, they are below the line, so the line is underestimating their amount of carbohydrates relative to their calories. Perhaps there's an explanation. Let's replace these plots with the same plots, but this time there are different symbols and colors for the different types of foods that Starbucks sells. The blue circles are bakery items, the pink items are all petite or small items, and we can see that they all have a relatively small calorie count. And now we can also see that the 2 points that the model doesn't explain well are red squares, which are bistro boxes. These are both light meals that are high in protein. They are tuna salad and salumi and cheeses, and they have a fairly high calorie count. But the amount of carbohydrates for these food items is much lower than this calorie count would predict, compared to other Starbucks food products. This illustrates a common error made in carrying out regression. The common mistake is to treat data from different groups as if they all came from one big group. In this case, the type of food item is a lurking variable. That is, it is an important variable that helps explain the relationship between carbohydrates and calorie count, but it hasn't been accounted for in our previous analysis. We can see that almost all of the bistro boxes have negative residuals, so the regression model overpredicts the amount of carbohydrates in these items relative to the calories. On the other hand, most of the bakery items have the opposite problem. Their residuals are mostly positive, so the regression model for them is underpredicting the amount of carbohydrates from the number of calories. A model that takes the type of food item into account would be a better model. Log transformations are extremely useful in statistics for a variety of purposes. Many variables naturally have a right-skewed distribution, and a log transformation of these variables can result in distributions that are more symmetric. In regression, log transformations can help make the relationship between two variables more linear, and it can sometimes solve problems with increasing or decreasing variance. There are many other transformations that could be considered. For example, the square root or reciprocal transformations are commonly used. But the log transformation often results in analysis that is more easily interpreted, because many variables naturally change in a multiplicative way.